The second problem then. The second problem, so the second problem was, let's see, the second problem was named minimum longest path. And the problem basically it gives us a DAG. It tells us that it gives us a DAG. So something like this, but a directed graph where some edges point to other edges. But importantly, there are no directed cycles. Each edge has some label. So each edge has some label. There are labels on the edges. And we would like to compute, what do we want to compute? We want to compute for each vertex, we want to compute two quantities. The first thing we want to compute is just the length of the longest path. The length, when I say length, I mean the number of edges. So the labels are not the total length of the labels, but like the number of edges. So the length of the longest path from this vertex. But then also, we don't just want the longest path. We want the sum of the labels of the lexicographically minimum longest path. When I say lexicographically minimum, what we're going to do is like, there might be multiple longest paths coming from a single vertex. So we're going to consider all of them. For each one, we're going to consider all the labels on that path in order. And then we're going to pick the one that has the lexicographically smallest like array of labels. So to give a quick example, the sequence of labels 2, 4, and 5 is considered lexicographically smaller than 2, 10, and 3 because the first characters match, but then the second character 4 is less than 10, so we stop the comparison there. So you basically compare them like strings. That's the definition of lexicographically smallest. Okay, so how can we approach this problem? Oh, and the bounds, the constraints, I believe, are, let's see, n and m are up to, for constraints, it's just n less than or equal to 2 times 10 to the 5, and m less than or equal to 4 times 10 to the 5. Okay, so the first thing we could do, computing this first quantity is a relatively standard problem. This is a dynamic programming on DAG, and it's kind of like almost like one of like the introductory examples for this concept. You basically so on a directed acyclic graph, there is an imposed order that you can do dynamic programming on. You basically just like do dynamic programming in a topological order. So like this one depends on this, and then this one depends on these, and then this one can be computed based on once this was computed, and this one can be computed once both of these are computed. And because there are no cycles, there's always like a valid topological order that we can process these states in. And then we just compute a dynamic programming where it's something like dp of u is equal to 1 plus or the maximum over all v that are adjacent to u of dp of v plus 1, where dp of u denotes the length of the longest path starting from u and going some amount, right? So this recurrence is basically, we're taking each vertex, we're considering each of the choices of where to go next, and we're taking the longest path from that point. So that's pretty standard. The second part is the non-standard part. So we want the sum of the labels in the lexicographical minimum longest path. And we need this for each vertex. So if you think about this for a bit, you will realize that there might be a weird cases where, so if you have a case, like for example, this vertex has 2 outgoing edges, 2 other vertices, and their paths, let's say both of these are optimal. So like from both of these, there are paths of optimal length. So you can choose to go through either of these. And one of these has label 3 and one of these has label 4. Well, then we're done because the one through label 3 is going to be lexicographically smaller. So of course we should take that one. But suppose they have the same label, they both have 3. Well, then just looking at this edge is not sufficient. So we have to like kind of look like one step further, right? So maybe now we look at the next one. Maybe this one has like some outgoing edges. This one has outgoing edges as well. And maybe let's say these labels are like 4, 10, 7, and this one has 3 and 4. So in this case, clearly the 3 and the 3 is optimal, so we just stop, and this is the optimal path. But like, let's say this 3 wasn't here, and this was instead a 5, then now we have to, both this 4 and this 4 are possible. And so we kind of have to keep looking. And so in general, like this might blow up to like an n squared procedure if we keep like going down and comparing the paths until we get one that is better than the other. So we can't compare the entire sequence. That is not really feasible. So we need some sort of way to like succinctly represent the information of which path is lexicographically smaller than the other one without like going down the entire sequence. And so you might try to come up with some heuristics that don't work. For example, you might think like, okay, I just compare the minimum sum instead. That isn't correct, although that passes an alarming number of test cases. But something that does actually work is to consider ranks. So here's the idea. For anything with a DP value of 1 is going to transition from something with a DP value of 0. Anything with a DP value of 2 is going to transition with anything from a DP value of 1. Something with 3 is going to transition off of something with 2, and so on and so forth. And so this kind of motivates processing the vertices in increasing order or in these layers depending on the DP value. So base case, when DP is equal to 0, that's pretty straightforward. Any vertices with DP equals 0, their lexicographically minimum path will just have sum of 0. Now let's consider DP of 1. So DP of 1 is going to have some vertices in this layer. They are going to point to stuff in the previous layer. And for each one, we are going to determine, we kind of just look at the outgoing edges, and then we're going to determine, basically, let's say this one has 1, and this one has a 2, and this one has a 1, right? And then DP of 3, or DP of 2, let's say, it's going to be something similar, where we have vertices up here, point down to here, and let's say, like, this one has a 1, this one has a 1, or this one has a 2, I don't know, I'm just making up some values. Say this one has 3, this one has 2, and this one has 1. Now, we don't want to encode each of these as like a sequence of length 2, like 1 and 1, or 2 and 1, or 3 and 2, right? Because that's the whole point. The whole point is trying to avoid that. So what we do is, after processing one of these layers, we reassign each vertex a relative rank within its layer of its sequence. And so here, I'm going to show you an example. So these all have the same relative ranks because they're all nothing. These I'm going to reassign to relative ranks of 1, 1, and 2. So all this means is that this one and this one both have equal sequences, and this one has something that's lexicographically larger. Then in the next one, now we have 1, 1, 2, 1, 3, 2, 2, 1, and 2, 1. Or I think this is I think I wrote a 1 here. So now I'm going to, again, instead of like storing like these as sequences of length 2, I'm going to reassign all of them like ranks. So 1, 1 is the smallest one. So I'm going to reassign this to rank 1. 2, 1 is the next smallest. So I'm going to reassign both of these to 2. And 3, 2 is the largest. I'm going to reassign this to rank 3. And so now you can see that like this, now you can see that at each step, I'm always assigning everything inside the layer a relative rank of how it compares to the other vertices within the same layer. And so now when I consider like multiple equal edges coming out of a vertex when trying to recover the path, I don't need to look at the entire sequence. I just need to look at these relative ranks. And if they're the same, then I know they have exactly the same sequence. If they're different, then whichever one's smaller is going to be lexicographically smaller. So I take that sum. And so now I've reduced the work to of computing the sums of lexicographically smallest paths for each vertex to also just n plus m. And so in total, this entire algorithm works in n plus m. All right. So any questions on the second problem?